Okay, now, if the pendulum motion is x2, 0 equals 0, and we picture that like so. Okay, position is 0 at t equals 0. Looking at the graph, we see that the position is going to start increasing. It's going to increase up to some point because t is increasing and the exponential hasn't decreased all that much yet, okay? But at some point, the decreasing exponential is going to overpower the increasing t, and you're going to hit a maximum. And you can figure out the t max and the x2 max, the time at which that occurs, and the position at which it occurs, just by doing a first derivative test on the x2 function. Very straightforward. Okay? Good practice. I recommend you do it. I'll probably throw in a problem where you have to do that. So, what happens? Well, you can tell here you've got a non-zero velocity at this point. If you didn't, well, you'd have no restoring force and no drag force, right? No restoring force because x is 0. And you're not displaced from your equilibrium position, and no drag force because it's not moving, right? So it's just going to stay there in that case. But clearly, that's not the case. It's got a velocity because the velocity is a derivative of your position, and it's clear you have a positive slope here, right? So it's clear that at this point you have a positive velocity, a non-zero positive velocity. And again, that's a good thing because otherwise you're not going to go anywhere. It's just going to stay there, okay? Now, what's going to happen? You're going to, well, your position increases up to x2 max, and then it starts decreasing again. Well, so we're going to go out to this point, and that's going to occur at the t max that you get by doing your first derivative test and so forth. Then, since you're out here, well, you got a restoring force because you're away from equilibrium. You got a force pulling you back. Okay? You have no drag because your maximum position, your velocity is 0. And of course, the slope of your graph is 0. That's your velocity, and you know that goes back to your first derivative test and so forth. So make sure we understand the connection. But it is going to start moving back then. It's got a non-zero net force back toward the origin. And it's going to start moving back just as fast as it would if there was no drag. But as soon as it develops velocity, then the drag starts kicking in. So you're going to move from here back, according to the graph, just back asymptotically once more approaching the origin, just as you did up here. But the function is a little different because of the t. Okay? And again, the m, k, and gamma are matched up in such a way that as you approach 0, you're going to have a point here where you have an inflection point here, right? Okay, what happens at that inflection point? Well, at that inflection point, this is where your drag force starts overpowering your restoring force. Okay? So the thing is speeding up to this point because your restoring force is dominating your drag force. Okay? But now it's moving so fast that the drag force balances the restoring force and overcomes it for the rest of the motion. But the drag force and the restoring force are so well balanced that they approach 0 basically along the same tangent line, okay? And you have an asymptote. You never get there, but you approach it arbitrarily closely, okay? And that's kind of your interpretation. So the one thing I've got here that wasn't there, your inflection point. That's where you start slowing, because that's where your slope stops getting bigger, okay, in the negative direction, that's where your velocity or your speed reaches its maximum and then starts decreasing, okay? The drag matches restoring force. So you want to think through that and see how it works, okay? Now, we still have plenty to talk about, but we're out of time. What happens if you do linear combinations of these two functions? What's it look like if you add this one to this one? You know, just use constants one, you know, do a linear combination where both constants are one, right? What's the graph going to look like? Well, if you think about it a little bit, it's going to, there potentially could look like this. Okay? So is it this? Or is the slope here less than the way I drew it, right? And it probably is. Of course, this isn't a very good graph here. Again, it's wobbly. But if this slope is less in magnitude than this one, then it could just be like this, but it's not a pure exponential. Okay? In other words, if this negative velocity exceeds the positive velocity you have here, okay? Well, you could have either behavior. If the negative velocity exceeds the positive velocity, just add a bigger multiple to this one and you can get this, right? And if the positive velocity exceeds the negative, add more of x1 and you could still get this, okay? So anything in between this and this. And then ask yourself, well, what does the motion look like in these cases? Well, in this case, it's going to be very much like just what we get for x1, but it's going to be a little bit modified. In this case, it's a lot like what we get here, but we're away from the origin, and then we give it a kick. So it goes out a little ways and comes back. That's how we model that case. So combinations of x1 and x2 will match anything that can happen with that perfectly damped pendulum, the critically damped pendulum, okay? And think through how, just intuitively in terms of the pictures. The algebra is not that difficult. We can add these functions and we can apply initial conditions, and that's not particularly hard. But understanding what that tells us about the motion is the critical thing.